Dear students, welcome to this lecture on the controllability of linear time invariant control systems. So, in this lecture we will see the definition of controllability and a necessary and sufficient condition for the controllability of a linear autonomous dynamical system or control system. So, controllability deals with the concept of controllability deals with the ability of a dynamical system to reach any arbitrary final state from any arbitrary initial state during a finite time interval using a control function. So, this concept is called the controllability of the control system. So, to understand the controllability concept, let us consider a simple example. So, let us consider the dynamical system dx by dt is equal to 2x and initial condition x of 0 is x0. T is the time variable and x of 0 is the initial condition given. Then we can easily see that the solution x of t or the state of the system at time t, it is given by e to the power 2t into x naught. So, here we can see that if t is the final time, any finite value capital T, then the final state x of capital T is e to the power 2t into x naught. So, what we can see here is this is the t axis and the x of t. So, at t equal to 0 the value is x naught and when t equal to capital T the function reaches the state x1, let us call it as x1. So, we can see that only this particular x of capital T can be reached by the system if you start with the initial condition x naught, because there exists a unique solution for this and so no other final state can be obtained. But in this case, if you consider a control system with the same dynamical system, if you include the control term u of t with the initial state x naught, then we can see that the solution x of t is given by e to the power 2t into x naught plus 0 to t e to the power 2 t minus s u of s ds. Now, at the final time instant capital T, we will get the final state x of capital T is given by this expression e to the power 2 into capital T minus s u s ds, it gives the final state of the system. Now, we are free to choose the control function u of t. So, by selecting a suitable u of t function, we can get any arbitrary value for x of capital T. So, if x1 is any arbitrary vector, is any arbitrary, here x1 is a real value. So, any arbitrary value, then we can get then using the control, let us select the control function u of s as e to the power 2 times s minus t. If you substitute in the place of u of s multiplied by the function x1 minus e to the power 2 capital T into x naught by t. So, we can see that if we substitute this u of s function in the inside the integral, we will get, then we get x of capital T will be equal to x1. So, it is the simplest way of selecting a control, so that the final condition is a arbitrary value x1. So, this is the concept of controllability. If you are able to find a control function, so that the final position x of t is any arbitrary given condition, then the system is called controllable. So, we will see the definition of the controllability. But before that, let us consider this example again. X1 of t derivative, that is x1 dot equal to say 2 x1 of t plus a control function, and another variable x2 dot t is, let us say, x2 of t, and some initial condition x1 at time t equal to 0 is a value, say alpha 1, and x2 at 0 is alpha 2. So, in this case we can see that in whichever ways we select the control function u of t, the second variable x2 of t can never be controlled as we wish, because if you solve this equation, we will get, solving the above equation, we will get x2 of t is e to the power t into alpha 2. So, any final time we take x2 of capital T is a constant single value, except this value we can not get any other value for x2 of capital T. So, the solution of the system or the state variable x of t, which is the vector here, x1 of t, x2 of t. So, this cannot be controlled as we wish. If you assign arbitrary final position for x1 t and x2 t, we will not be able to reach that position, because x2 of capital T is a fixed value, only one value can be reached always. So, this system is not controllable. So, if you call this system to be 1, then the system 1 is not controllable. Because whatever control we substitute, we will never reach any arbitrary final condition. We will be able to reach only a fixed final condition for the variable x2. So, the definition of controllability is given here. So, the linear time varying system, general system, we take x dot of t equal to a of t x of t plus b of t u of t, where a of t is a n cross n matrix and b of t is a n cross m matrix. So, this system is said to be controllable if for any initial time t0 and any initial state x suffix 0 and given arbitrary state x1 in Rn space, x naught belongs to Rn, then there exists a final time capital T and a control function u of t such that x of capital T is x1. So, that means we will be able to find a control function u of t and a final time capital T, so that the final position of the solution is x1, which is a arbitrary value in the state space. So, if this happens, then we say that the system is controllable. And if you are not able to find a control function like this for any arbitrary x1, we will not be able to find a control, then we call it as uncontrollable system, but it does not mean that we cannot reach any final condition. We will be able to reach some final condition x of capital T, but all the points in the space may not be able to will not be able to reach by the system. So, the condition for controllability of the autonomous system, that is the matrix A and B are constant matrices. So, is given by the rank condition. The necessary and sufficient condition for controllability of the system 1 is the rank of the matrix B, A B, A square B, etc., A power n minus 1 B is equal to n. Here A is the n cross n matrix and B is n cross m. So, we have n cross m matrix n times. So, the size of the matrix given in the bracket is n cross m into n. So, the maximum rank for this matrix is n, the smallest, the minimum number out of these two. So, maximum rank can be n, but the system will be controllable if and only if the rank is equal to n. So, that is called the Kalman theorem. This is called the Kalman condition for the controllability of the system 1. So, let us prove it. The necessary condition, if the system is controllable, then we have to prove that the rank of the matrix U is equal to n, where U is given by B, A, B, A square B, A power n minus 1. So, this is a statement of the theorem. Now, if the system is controllable, but the rank is less than n, then we will arrive at a contradiction in the following way. So, if the rank of U is less than n, then there exists a vector alpha in Rn, the state space, and alpha is non-zero such that the transpose alpha dashed into U is equal to 0. So, U is a mapping from R m n to Rn. So, we can show that similarly the transpose U dashed is from Rn to Rmn. So, if the rank of U is less than n, the rank of U dashed is also less than, both are the same rank. So, we will get a vector U dashed alpha equal to 0 and alpha not equal to 0. If rank is less than n, this will happen. If you take the transpose, we will get alpha dashed U is equal to 0 for some non-zero vector alpha. So, the system is controllable is given here. The solution of the equation 1 is given by this, where e power a t minus t naught is the state transition matrix, and the solution at the final point capital T. So, if you substitute in the equation 3 the solution, if you put t equal to capital T, the final time, and x of t equal to alpha and x naught equal to 0, because the system is controllable given. So, for any initial condition and any final condition, we will be able to find a control U, because the system is controllable. So, now we substitute the arbitrary value alpha for the final condition and the 0 condition for initial. So, from equation 3 we will get this alpha equal to integral t naught to t e to the power a t minus s bu s ds. So, directly we can check. So, and the system is controllable. So, we will be able to find a control satisfying the above equation 4. Now, using Cayley-Hamilton theorem, the any function of the matrix, here it is the exponential a t minus s, it can be written as a polynomial expression of polynomial in the matrix A. So, this expression is due to Cayley-Hamilton theorem. So, if you substitute in the place of e to the power a t minus s, that polynomial expression, we get alpha equal to integral t0 to t of this expression. Now, we can bring this B matrix inside the bracket, we will get A naught into B, A1 into AB, etc. And this A naught, A1, A n minus 1, all these are scalar functions. So, it can be written in anywhere, they are commutative. So, we can write the first term as B into A naught s into US, this function u of s also can be brought inside, and then second term is AB, and A1 of s can be written here multiplied by u of s. So, we get this. Similarly, a power n minus 1 b into a n minus 1 of s into us, everything is integrated with ds. So, this expression can be written like this. The first term can be written as, because B is a constant matrix, it can be taken out, we will get t naught to t a naught s us ds. Similarly, the second term, it is a b integral a1 s us ds plus etc. So, here we can see that U is a m cross 1 matrix. So, when we do the integration t naught to capital T of this expression, we will get a vector here, that is B is the matrix. After doing the integration and putting the limit, we will get a constant vector. So, we will call it as V10, V20 etc. Vm0 and plus AB, again we will get a constant vector after doing the integration, that is V11, V21, Vm1. So, all these vectors are in Rm space, m vector. So, we will get the expression like this. This 0 indicates that it is due to the coefficient, indicating the coefficient A0, and if the coefficient is A1 of s, we integrate, we call it as V11, V21 etc. So, we get a expression of this type. So, this can be further written as this one B a b a square b etc. a power n minus 1. So, the first vector b into the first vector plus a b into the second vector etc. So, the same previous expression can be written in this particular form. So, it is nothing but the matrix U which we considered, and this is a vector, and U is a mapping from R m n to R n space. So, alpha belongs to R n here, and that is equal to this expression U into, we can call it as a matrix V, the vector V. So, U into V is equal to alpha. So, this is the equation we are getting, alpha equal to U into the V vector. Now, if you multiply both sides by alpha dashed, we will get alpha dashed into alpha is alpha dashed U into this, but our assumption is U is singular. Therefore, the vector alpha dashed exists, so that alpha dashed U equal to 0. So, this term becomes 0. So, what we get is alpha dashed into alpha, which is norm of alpha square, that is equal to 0, this because of this one. So, this implies alpha is a 0, it is a contradiction. So, this implies that U has rank n. Okay. So, now we will prove the sufficient condition. So, let us assume that rank of U is n and we want to prove that the system is controllable. So, let x naught x 1 be arbitrary vectors in Rn. So, if the system is controllable, we will be able to find a control function. So, that the initial condition is x naught and final condition is x 1. So, our assumption is rank of U is n. So, when we write the solution of the system and put x of capital T, that is when we put t equal to capital T in the solution and writing x 1 as final condition, x naught as initial condition, we will get the equation like this: x 1 equal to e power a t minus t naught x naught plus integral e power a t minus s b u s d s. Again making use of the same technique which we used earlier, using Cayley-Hamilton theorem, e to the power a t minus s can be replaced by the polynomial expression, and then making use of the integration we will get a similar expression. The same expression we will get this way. Only thing is, in this case we do not know what is the vector v 1 etc. This vector v is unknown, and x naught and x 1 are two given arbitrary vectors. So, the left hand side is arbitrary vector in Rn, because x naught and x 1 are arbitrary vectors. So, we will get the equation in this form. If you write the left hand side vector as beta and the vector given in the right hand side is gamma here. So, we get a equation beta equal to u into gamma, and the rank of u is equal to n as given in the sufficient condition. So, we will get a solution for this expression. So, u gamma equal to beta, if rank of u is n, there exists a gamma which satisfies this equation. So, the system is controllable because we will be able to get a gamma function. We get the gamma value which is given by this vector v 1 0, v m 0 etc. And then v 1 1, v m 1. So, lastly we will get v m. So, we get the vector gamma. It is it is not a unique solution, there will be infinitely many such solution, because the size of the matrix U is a mapping from R m n to R n. So, for every given vector beta in R n, you will get many solution vector gamma belongs to R m n. So, that u gamma equal to beta because of the size of the matrix. So, now each value, for example, if you take v 1 0, it is nothing but integral t 0 to capital T a 0 of s u s d s, is not it, v 1 0 to v m 0. So, this vector is given by this expression. Similarly, v 1 1, v 2 1, v m 1. So, this vector is given by t 0 to t a 1 s u s d s. So, etc. So, when we have the gamma vector with us, we can find the function u of s satisfying these conditions because of the relation given by this gamma and the u function. So, if you are able to get the gamma vector, we will be able to get the control function u of t using this relation. So, the system is controllable, that is for any given initial condition and any given final condition, we are able to find a control u of t for this control system. So, the system is controllable here. So, in this lecture we have seen the necessary and sufficient condition for the controllability of an autonomous system. So, in the next lecture we will see the necessary and sufficient condition for the controllability of non-autonomous system, that is time varying system. Thank you.